Alrighty, ladies and gentlemen, let's get started with our big ideas. Lesson 10.5, page 438. If you are an 8 general student, and lesson 16.5, page 738 for those in the 7th accelerated class. So now we're going to move into the scientific notation part of this unit. And we are going to read numbers in scientific notation, and we're going to write them in standard form. Our essential question: how can you read numbers written in scientific notation? Now, I know you took notes from the top of the appropriate page based on the book that you're looking at on scientific notation. And you took some notes down, and the example in the book is different than the example I'm going to show you. But here's the thing you really need to know about being able to look at and read scientific notation. First, you have this number. This number is a factor. There is a factor here. A factor is a number that is multiplied by another number. They are both called factors. Well, this factor right here is a factor that, when we write this down, has to be a number that is greater than or equal to 1, and it has to be less than 10. Okay? So right here, greater than or equal to 1 and less than 10. It has to be. That factor has to be in that form, or we do not have a number written in scientific notation. And then that factor, of course, because it's a factor, it's multiplied. Now they put an X. We don't like X's. You can use a dot if you want, but we're going to use they're going to use an X for being written in scientific notation. And then it's multiplied by a power. And this power is very specific in the fact that it has to have an exponent that is an integer. Okay, the exponent has to be an integer. Now you should remember your integers. Integers are made up of our natural numbers. Those are our counting numbers, 1, 2, 3, etc. They're also made up of our whole numbers, which we're going to add a 0 to that. And then they're made up of the opposites of our natural numbers, the negatives, -1, -2, -3, ... in that direction. So if it is one of those numbers, it is an integer, and that integer can be in the exponent of the power. So our factor has to be greater than or equal to 1, less than 10, and our exponent has to be an integer. So the first thing we're going to do is we're going to look at some numbers written and see, are they in fact written in scientific notation? It says tell whether the number is written in scientific notation and explain. So the easiest way to do that is to look at the factor first. Is this number, we're looking at number 1, 2.5 times 10 to the negative 9th. Is 2.5 greater than or equal to 1? Yes, it is. Is it less than 10? Yes, it is. Do we have an exponent that is an integer? That also is yes. So that means number 1, 2.5 times 10 to the negative 9th, is written in scientific notation. Let's look at number 2, 0.5 times 10 to the 5th. Looking at 0.5. Is that greater than or equal to 1? The answer to that is no. So that is the explanation as to why that number is not written in scientific notation. Our factor is not greater than or equal to 1. Going to example number 3, 51 times 10 to the 0. So 51, taking that factor, is that greater than or equal to 1? And the answer to that is yes. Is it less than 10? Unfortunately, the answer to that is no. So it is not written in scientific notation. I want to continue on with this one. Can I have an exponent of 0? Is 0 an integer? Well, hopefully you say yes, because we just did it on the previous page when I was talking about integers, and I listed those natural numbers, the whole numbers, and the integers. And so yes, that 10 to the 0 is acceptable. Excuse me. Example number 4, 8 times 10 to the negative 21. Is our factor 8 greater than or equal to 1? Yes. Is it less than 10? Yes. Is our exponent an integer? Yes. So this number is in fact written in scientific notation. So let's move right along, writing the number in standard form. And number 5 says 8.45 times 10 to the negative 5th. Now, ladies and gentlemen, multiplying by a factor of 10 moves the decimal. You've always done this. If I have the number 8 and I multiply it by 10, you move the decimal one place to the right and you add a 0. Well, that's what we're doing with these multiples of 10. These powers are always powers of 10. So we're just adding zeros or basically moving that decimal right or left. And if you have a negative exponent, you might want to write this down. Negative exponent moves the decimal left. Well, that only makes sense because on a number line, negative numbers go to the left, right? Positive exponents move the decimal right. All right. It just so happens that they move left to right the same number of places equivalent to the integer in the exponent. So if we're looking at 8.45 times 10 to the negative fifth, I'm going to rewrite that number. 8.45 times 10 to the negative fifth. And I'm going to move that decimal, I'm going to move it 5 places, because that's what it tells me. And since it's negative, I'm going to move left. So I go 1, 2, 3, 4, 5 to the left. I put my decimal. I've got to hold my place value, so I annex some zeros in there. And my final answer is 0.0000845. All right? Now I'm going to stop for just a second. This is going to take a few minutes of our notes, but I want you to understand why we're moving it left or right and what this really means. We had a lesson not too long ago on negative exponents. So if I have this exponent of 10 to the negative fifth, we were told that when we simplify that, how do we do so? To get rid of that negative, we rewrite that as its reciprocal with a positive exponent. Well, if you simplify that out, you would get 1 over 100,000. Now, if you take a calculator and divide 1 by 100,000, obviously you're going to get a decimal. In fact, you're going to move that decimal from the right side of the 1, you're going to move it 5 places to the left. There are 5 zeros in 100,000, so it moves the decimal 5 places to the left because this was a negative exponent. So if I do that one with our first problem, 8.45 times 1 over 10 to the fifth, that's taking 8.45 and dividing it by 100,000, which moves the decimal 5 places to the left. And we annex our zeros in there, and we get the same answer. All right, so now we're going to move right along. I am going to erase a lot of this. Okay, and we're going to move right along. Number 6, 9.3 times 10 to the 10th. We learned that it's a positive exponent. Decimal's going to move to the right for the same reason of multiplying by a power of 10. So 9.3, I move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom, put it right there. Annex some zeros in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 93. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the answer to that. 9.3 times 10 is 93, what is that? Billion. 93 billion. All right, going to our next one. 1 times 10 to the negative 9th. Well, here we have the number 1. And the decimal we know is right here. So we're going to move it, 9 places. And we're going to move it 9 places left because it's negative. 1, 2, 3, 4, 5, 6, 7, 8, 9. Put our decimal right there. Annex some zeros. And our final answer is 0. 1, 2, 3, 4, 5, 6, 7, 8. Oops, that's a 0. And then we have a 1. And so that is our 1 times 10 to the negative 9th written in standard form. We have 9.93256 times 10 to the 4th. Times 10 to the 4th means moving it 4 places to the right. 1, 2, 3, 4. I can put it right there. So my final answer is 99325, 99,325.6 is that number written in standard form. Very good. Moving right along. Comparing numbers written in scientific notation. Writing the numbers in order from least to greatest. And so the first thing I'm going to look at, if I want to go least, I want the one with the largest number that's negative in the exponent. In other words, this negative 8, because this number is going to be a big old honking decimal. So that one's going to be the smallest one. 2 times 10 to the negative 8. Then, well, the next negative number, we only have one more, is that one. 4.5 times 10 to the negative fourth. Okay, so that's the easy part. Now we got these two numbers, 3.54 times 10 to the fifth and 6.2 times 10 to the fifth. Well, I already know 10 to the fifth and 10 to the fifth, that's the same. And I know that 6.2 is greater than 3.54, so I'm going to go with this one as the smaller one, 3.54 times 10 to the fifth, and then we have 6.2 times 10 to the fifth, and then of course the biggest number out here is 2.98 times 10 to the sixth. So looking at those exponents to tell me how big is that number going to get. And if I have the same exponent, then I go back to the factor and I compare the factors to see which number is bigger. Our last example before our quick write, real life application, the mass of a the mass of a particle of dust is 7.53 times 10 to the negative 10th kilograms. If a pair of shoes has 1,000 particles of dust on them, how much does the dust weigh? Okay, well the first thing I'm going to do is I'm going to take 7.53 and I'm going to multiply it because I'm going to multiply it by 1,000 because I want 1,000 of those. And so that means I'm moving it, so 7,530, and that's times 10 to the negative 10th. And so now I can write that in standard form by moving that decimal 10 back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6. So how much does it weigh? 0.123456750 kilograms. Well, that decimal is quite small. That's how much it weighs. All righty. Ladies and gentlemen, our first quick write. You might want to pause it so you can write all these down and then do what they say. Either write them in scientific note, are they written in scientific notation? And B, write them in standard form. Ladies and gentlemen, it's always a pleasure. Come back for video number 2 on writing scientific notation. All right?